Okay, I think that's everybody. Let's start. Today's lecture number 12, durability 1. Okay, we have 3 lectures on durability of concrete. Okay. Before we do that, let's talk about the midterm Tuesday next week. So I will upload the midterm to Lorima before our time for the midterm, which is the same time as our class. So 3:30. You have 1 hour, 15 minutes to finish. Okay, you should also submit to Lorima. Anyway, I will give you more details for the midterm, and it is open book, open notes. Okay, covered from lecture number 1 to lecture number 10. Okay. So durability. Okay. The definition of durability is the durability of Portland cement concrete defined as its ability to resist varying action, chemical attacks, abrasion, or any other process of deterioration. Okay. So durable concrete will retain its original form, quality, and serviceability when exposed to its environment. Okay. In this class, we will learn how we can make durable concrete. And the second question, how do we balance service life and cost, we will not be discussing details in this class. Okay. But we can understand how and why a concrete will have durability issues and how we can prevent and reduce the potential for durability problems. Okay. So there are many factors affecting concrete durability, including uncontrollable factors, okay, such as environmental conditions. Okay. Controllable factors, type of cement we use, okay, the type of aggregate, for example. So this belongs to concrete constitute, mixed proportions. What is water cement ratio? How much percent we use pozzolanic materials? Okay. Manufacturing process, how much compaction, how we can prevent bleeding and segregation, how much air percentage we use. Okay. Curing conditions, how long we cure the concrete. For example, structure design and detailing, how much load the concrete will experience, and what's the size of the rebar, spacing of the rebar, and what is the rebar covering, or the thickness of the concrete, protect the rebar from corrosion. Okay. So this is belong to detailing and design. So cracking and deterioration. When we have pristine concrete, there's no cracking. Okay, as long as the concrete is casted accordingly. Then the crack will occur due to loading or deterioration, okay, such as shrinkage. Okay. When concrete has crack, the crack will opens up because water will bring harmful materials inside the concrete and do further damage. And the loading will, again, opens up the crack. Okay. So the crack will initiate deterioration, and the further deterioration will facilitate further cracking. So eventually, concrete will fail. Okay. The rebar protection, the concrete cover will falls off. Okay. So here talk about water and the concrete. We know for concrete hydration, we need water. So without water, the cement will not hydrate. So we cannot make concrete without water. Okay. But you will also know almost any type of deterioration, physically or chemically, will involve with water. Okay. So let's look at the water molecule in the details. So water molecule has a polar molecule, okay, which means it has two ends, and the two ends has opposite electrical charge. Okay. And because of that, the water molecule will orientate along the surface of the capillary pores inside the compound. Okay. And when water lost, we have capillary tension, and that will cause shrinkage of concrete, as we discussed in lecture number 11. Okay. So we did that Tuesday this week. So shrinkage is caused by capillary tension. That is because water is a polar molecule. Okay. So water is essential for cement hydration. Cement will not react without water, and will not have concrete without water. And also, after we cast the concrete, we know curing is very, very important. The longer the curing, the better for the strength and durability. Okay, so at initial age, water is good for concrete. Okay, so longer the curing, the better for concrete. Okay. However, after the concrete achieve its design strength, then water is not good for concrete because almost all the chemical and the physical attacks will involve water. Without the water, what concrete will last very long time. Okay, because water is agent of deterioration. If you move in and out of the pores, okay, water will also serve as a vehicle for transport for aggressive ions such as chloride. Chloride, for example, will cause corrosion of reinforcement. Water may also bring sulfate from the soil or underground water into the concrete, and we have sulfate attack. Okay, so is water good or bad for concrete? Depending on, at what age. At early age, we do need water. Without water, we cannot make concrete. But at later age, water will cause all kinds of damage in concrete. Right. So the first type of durability issues is frost damage. We also call that freeze and thawing. Okay. Before we do that, let's review three important properties of water, H2O. Okay. The first one is liquid water has higher density compared with ice, or solid water. Okay. This is kind of unique property of water. Other materials, the liquid is less denser compared with solid form. Okay. The other property of water is solid water on ice is pure H2O. This means when we have a solution of certain materials, such as sodium hydroxide solution, and if we reduce the temperature slowly, okay, and if we have a mixture of water and ice, in that case, the ice contains pure water, and all the salt go to the remaining part of water. Okay, so that's the reason why the icebreaker in the North Pole is pure water. Okay, and all the salt go into the liquid part. Of course, if we further reduce the temperature and everything become ice, then the salt will go nowhere and stay in the ice. Okay, as long as we have a combination of water and ice, and then the ice will be pure water. All the salt is going to the liquid. The third property of H2O is if we increase the pressure on the ice, okay, and the smaller pores will reduce the freezing point of water. Okay, so that means if we increase the pressure on ice, for example, we step on ice, then the freezing point will be lower. So that means the ice may be melted with higher pressure. And also the water in smaller pores will have lower freezing point. Okay. So that's another important property for water. And then let's look at the freezing damage possible in concrete. So the first one is internal damage, okay, which is ice formation within the capillary pores, so within the cement paste. Okay. We also have surface skating, which is the damage only on the top surface of concrete. This is due to de-icing solution. During winter, to melt ice, people will put a de-icing solution. So that kind of salt, which will decrease the melting temperature, freezing temperature of ice. Okay, so we use that commonly during the winter for the concrete pavement. So that will only cause surface damage in the concrete. So we call that skating damage. The third type of freezing damage in concrete is called aggregate damage. When the aggregate is porous or has lower strength, then the aggregate may also be damaged itself. Okay. So let's look at the internal frost damage, which occurs in the cement paste. Okay. So there's several series which may help to explain why we have internal frost damage. Okay. Exactly which one is dominant, we do not really know. Okay. This is the potential contributing factors for the internal frost damage of concrete. The first one is the hydraulic pressure. Okay. So when ice formed, the volume will increase because the density of ice is lower compared to density of liquid water. So the volume of ice will increase. That will cause pressure rise in unfrozen liquid in surrounding areas. For example, here we have ice crystal formed here. The water surrounding the ice will have a high pressure because the ice volume will expand. So that may cause the concrete to crack. Okay. Another possible series is called osmotic pressure. Okay. So when ice formed, actually when we have a combination of ice and water, okay, and remember in the ice, all the salt go to the remaining water, and ice is pure H2O. So the remaining pore fluid will concentrate it because the salt will go into nearby liquid. So as a result, we have difference in concentration of these salts. Okay, so the liquid around the ice has a higher concentration compared to other part of the liquid. So the surrounding unfrozen point will drain, trying to balance the difference in this concentration of salt. That will cause the so-called osmotic pressure. Okay, so remaining water will drain to the liquid near the ice, so that will cause pressure to increase. That may damage the pores of the cement paste. Okay. And the third possible series is called crystallization pressure. That is when the temperature drops, the crystals, such as ice, will exert pressure on the wall of the pores. So that pressure from the crystallization may also cause the cement paste to crack. Okay, so these are three possible reasons we have internal frost damage. All right, so this is some picture of frost damage. As you can see, the cement paste will spout off, algae will be exposed, and the rebar may also be exposed. Okay. So this is so-called decracking. So decracking is caused by porous aggregate. So when the aggregate is porous and we have water moisture in this porous aggregate, and when temperature drop down, the aggregate may fail inside of cement paste. Okay, and that will form this kind of cracking patterns. We call that decracking. Skidding damage again is caused by de-icing solution. Okay, it happens on concrete pavement. When during the winter we put de-icing solution in the pavement, and that salt may cause damage in concrete. Okay. The possible reason for that is explained here. It only occurs when we have the liquid on the surface of concrete, okay, and only occurs when the liquid contains salt, a solute, for example, sodium hydroxide or other de-icing salt. And certain concentration will cause different type of damage. Okay. And to reduce this type of damage, we could introduce air entraining agent in concrete to reduce the possible skidding damage. And the reason for the skidding damage can be explained by the so-called biomaterial effect. Okay. So let's say here we have a pooled water. Inside that pooled water, we have salt. Okay. And we have concrete layers beneath that pooled water layer. When the temperature drops down below freezing, the water becomes ice, and that will form a well-bonded composite materials. So we have ice layer on top of the concrete layers. Okay. Here shows this is alpha ice, and it means coefficient of thermal expansion of ice, which is much larger than coefficient of thermal expansion of concrete. Okay. So that means when temperature drops down, the shrinkage of ice layer will be much more compared with the shrinkage of concrete. Okay. However, we have very good bond between the ice layer and the concrete layer. So when temperature drops, ice will contract more than the concrete. Okay. So the concrete will restrain ice from further shrinkage. So that will generate tensile stress in the ice. So the ice will crack due to this tensile stress. And the crack will somehow propagate into the concrete layer, but not very deep into the concrete. So only the top surface of the concrete. Okay. So when crack generated in the ice layer, sometimes the crack will propagate into the concrete layer somehow. So that's why we have this scaling damage, only limit to the surface on the concrete. And we can see here, this is caused by the scaling damage, and the damage is only limited to the several millimeter inside the concrete, so not very deep. And here show how air entraining agent can reduce the scaling damage. Okay. So the same concrete with no air entraining agent, so if we increase air content, so the damage on the surface is reduced, as we can see clearly from here. So to reduce frost damage, we can use air entraining agent that will generate tiny isolated air bubbles, which are empty. So that will release the stress coming from the expansion in volume. Okay. And I think we discussed this when we talk about air entraining agent. But here says decracking is not preventable by air entraining agent. Why that's the case? And remember, decracking is caused by frost damage of aggregate. Okay. If we introduce air entraining agent, that will introduce air bubbles in cement paste only. Okay. So decracking is frost damage of aggregate. So air entraining agent cannot prevent decracking. All right, so the first type of durability issues is frost damage. Okay. Any questions for this before we talk about ASR? All right, so the ASR is the one type of chemical attack. Okay. When we talk about aggregate, I think we mentioned about ASR a little bit. Okay. So ASR is a reaction between alkalis in cement and a certain type of silica in aggregate. Not all type of aggregate will have potential ASR, but certain type of aggregate. Okay. This is the cracking caused by ASR. Okay. We also call that map cracking because the pattern of the crack similar to maps. Okay. The cracking is generated from inside. Okay. Let's make ASR very difficult to control. Okay. So ASR has been known for a long time. The first ASR spawned around 80 years ago, okay, in California. Okay. So in the US, we have hundreds of affected dams, which is caused by ASR. Okay. If ASR happens, it is almost impossible to repair because again, ASR is generated within. So that's the reaction between alkali in a cement and the aggregate. So the aggregate is inside the concrete. So no good remedy to repair ASR. ASR is also called cancer of concrete. So the best way is to prevent ASR from the first place. All right. So here's another example from a damaged dam from ASR. You can see we have the reddish materials coming within the cracks inside the concrete. So that is the gel coming out of the concrete. Okay, so if you see something like that, you may double check if it's caused by ASR. Okay, so another picture of ASR. So the crack is generated within the concrete. So very hard, if not impossible to repair. Okay. So ASR is caused by alkalis, different type of alkali, potassium, sodium, calcium alkalis. They're gonna generate different type of gels. Okay. The silica is coming from aggregate. Okay. So alkali plus certain type of silica plus water will cause swelling alkali silica gel. So that swelling will result in cracking and spalling of concrete. And remember, the gel will not swell if the water is not available in concrete. Okay. So as long as there's no water in the concrete, even if we have a lot of alkali and if we have reactive silica, there will be no ASR. So this is the microscope. From optical microscope, we can see the gel around aggregate. So the gel is generated between silica in the aggregate and alkali from cement. So often we see the gel surround the aggregate. Okay, sometimes the aggregate will also crack. So does the cement paste. Okay, so this is the gel in the voids. This is the empty air voids. You can see the gel generated inside empty voids. So if we put air entraining agent, air entraining agent will generate tiny empty air bubbles. So that may be beneficial to reduce the stress caused by this expensive gel. Okay, so air entraining agent may potentially reduce ASR. Okay, so seen from scanning electron microscope, we see ASR gel looks like a cotton flower. Okay, the scale here is 2 micrometers, so very, very small scale. In 200 micrometer scale, we see the gel looks like this. Here is 100 micrometer, which is 0.1 millimeter. We see the cracking, okay, also in the ITG zone, so between the aggregate and the cement paste. Okay, and the crack may also pass through the cement paste and also can pass through the aggregate. Okay. Okay. So here are more information about ASR. Let's just read it together. So siliceous aggregate component react with alkali hydroxide from a per solution to generate a hydrosiliceous gel. Okay. Right, with different alkali, silica, and calcium cations. Okay. High concentration and volume of fluid must be available. So we need water, we need moisture for ASR to happen. Okay. The gel is osmotically active and expand when we have moisture. So that will create pressure and potential cracking in concrete. Okay. And sometimes you see the cracking across aggregate. Okay. And crack will extend to the surface of the concrete. Okay. And then when the crack reaches the surface, okay, and further vacuum will convert the gel into a mobile soil, okay, which will leak out and form the wettish deposit materials on the surface, as we see on the previous picture of the dams. Okay. And here it says calcium must be locally available for the gel to be sufficiently coherent to exert pressure. Okay, so we need calcium ions for the gel to apply the pressure. Pure classical gel has very low viscosity, so it will just dissolve in the pore solution, cannot cause the cracking. So factors affecting ASR from the part of aggregate composition is very important. So nature and percentage of reactive silica. Okay, some aggregate does not have silica at all, so we don't need to care about ASR. Even if the aggregate has silica, but if it's not reactive, we still do not need to worry about ASR. So if the aggregate has reactive silica, then the size of aggregate will be a factor. So smaller particle size will increase expansion because the smaller particle size, the interface between the aggregate and the cement will be higher. So we have higher potential for the reaction between alkali from the paste and the silica from the aggregate. Okay. And the amount used is also important. Okay. The more aggregate, the more potential ESR. Okay. And this table here shows us alkali reactive silica minerals and a certain type of glasses which may be reactive. Yeah. We have some other tests to check the potential of ESR for certain type of aggregate, which will be discussed in a moment. Okay. Here shows the study, the sample study. Even if all the rocks has the same chemical composition, but the ASR potential is also very different. Okay. From the cement point of view, because cement will contribute alkali, the alkali coming from cement. So the lower amount of alkali from the cement, the better for ASR. Okay. Sometimes people control the percentage of sodium hydroxide plus potassium hydroxide to a certain level if ASR is a concern. Okay. So here shows a method of following ASR reaction response by progressive removal of alkali from pore solution. So in this certain experiment, it monitors the concentration of alkalis, such as potassium and sodium. Okay. For the control mix, the concentration is pretty much constant. Okay. But for sample with ASR, the concentration of alkali will be reduced because they are consumed by the ASR reaction. Okay. The temperature of cement production may also be a factor because the temperature during the production of cement in the kiln will affect percentage of sodium oxide, okay, which is another type of alkali in the clinker. And moisture, so condition during curing. At early age, moisture curing is good because moisture curing will reduce the permeability. Okay. So lower permeability is better for ASR, actually for all type of potential durability issues. But later age, we should try to limit amount of moisture if possible, because no moisture, we don't even need to worry about the potential for ASR. Okay. So how to tell if ASR is present in a given concrete? So there's a different type of method. We can use optical microscope. Okay, we can see if we have a gel, as we did in the sample picture show you moments ago. Okay. We can also observe the pattern of the crack. If we see a map cracking on the surface of concrete, and also we see whitish gel coming out of the crack, so very likely it's caused by ASR. Okay. We can also use scanning electron microscope to see the microstructure of the gel, or we can check the chemical composition by EDS. So EDS is one part of test in scanning electron microscope. It can see a certain type of chemicals in the materials. And we could also use uranyl acetate test procedure. This is a very simple standard testing method by Federal Highway Administration. Okay. Does not need any microscope. Okay. We're going to talk about procedure, how to use uranyl acetate to see ESI concrete in a moment. Okay. Right. So the series for uranyl acetate testing procedure is here. Okay. Some or all of alkaline ions in ESI gel are exchangeable cations. Okay. So we use a solution of uranic acetate, which is the UO2. Okay. So these uranic ions may replace calcium ions in the gel. Okay. So we apply acetate solution, and uranic ions will replace calcium ions in the gel, and then we wash away all the excess uranic acetate, and then we examine the concrete sample use UV light. And uranic ions will fluoresce under the UV light, so we can see where the ASR gel under the UV light. Okay. As we can see from here. So after the procedure, under normal light, we don't see anything actually, but under fluorescent light, UV light, we see the gel inside these cracks. Okay. The whitish color is the gel. Okay. So from there, we can identify the cracking is caused by ASR. Right. Here is another commonly used test for potential ASR of aggregate. Okay, this is ASTM C1260. This is called mortar bar test. Okay. The mortar bar test, the procedure shown as here. Prepare the mortar test specimen according to the standard procedure. We prepare the aggregate, and we mix the mortar sample with a certain water to cement ratio. And then we insert the specimen into a 1 molar, this 1M, not 1N, sorry. So 1 molar sodium hydroxide solution. And the temperature is maintained as 80 degrees Celsius. The reason we insert the specimen in such a high concentration of alkali, such high temperature is we want to see the result quickly. So we measure the expansion of the mortar bar over only 2 weeks. And we measure how much the mortar bar expand. So beyond a certain level, so this is 0.015%, then we can see the aggregate will be reactive. Less than that limit, we see the aggregate is inert or okay. We also have ASTM C1293. This is concrete samples. For this test, we make a concrete sample instead of mortar bar sample. And we do not put the concrete sample into such a high concentration of alkali. And the temperature is room temperature, not 80 degrees Celsius. But we monitor the expansion of concrete specimen over at least a year. So take much longer time, but it's more accurate. Okay, so depending on if we want to see the result quickly, or if we want to see a more accurate result, you can choose ASTM C1260, this mortar bar test, or ASTM C1293, which is the concrete test. Okay. Okay, so we talk about the potential mechanism, the mechanism for ASR. Then let's look at how can we control the ASR. Okay, because ASR is caused by reactive aggregate with alkali from a pore solution together with moisture. So one way to control the ASR is to control the alkali concentration from the cement. Okay, control this part. So we can use, for example, low alkali cement, okay, or we can use blended cement. So blended cement is Portland cement together with slag or fly ash. So that will also reduce the alkali content in cement. Okay. We can also control reactive silica. So we control this part here. So we can do several things. We can screen aggregate for possible ASR reactivity by doing ASTM C1260. Okay. If the alkyd is not reactive, we don't need to worry about ASR. Okay. We can also use petrographic examination. Okay. Depending on the skill level of petrographer, okay, to see if the alkyd is reactive or not. So this is, of course, before we make the concrete. That's why we see it's important to prevent ASR in the first place. We can do the mortar bar test, the 12C ASTM 1260, or we can do the concrete test, ASTM C1293. Or we can, based on the local knowledge of previous example, if we used a certain type of alkyd before and we never see ASR, okay, then probably we can safely use that type of alkyd. Okay, so based on the service record of local experience. From mixed design point of view, we can reduce the water to cement ratio. We can use silica film to reduce the permeability of concrete and control the moisture. We can also alter the nature of alkali silica gel. We have certain type of chemical admixtures such as lithium and barium salt. Okay, so that type of salt will cause non-sweating lithium or barium silicate hydrate. So the gel will not expansive, so will not cause pressure in concrete. So no potential cracking. Okay. So here shows an example of expansion of mortar bar prepared with 1 molar of sodium hydroxide, potassium hydroxide, or lithium hydroxide. Okay. You can see for lithium hydroxide, the expansion value is lower compared with potassium. Okay. The reference is the control mix, which has no hydroxide. Okay. So more words about lithium-based admixtures. Okay, so the problem for that is lithium hydroxide may increase concentration of hydroxide ions. So, more hydroxide ions, which may be generate more potential ASR. Okay, we increase alkali concentration because of that. So if we do not use lithium hydroxide, we use lithium nitride, so that will not increase concentration of hydroxide. So lithium nitride is more effective compared with lithium hydroxide. Okay, and the reason for that is lithium will exchange other type of ions such as potassium and sodium and calcium. Okay, and the gel with lithium will not swell. Okay, so no swelling, no cracking. And the cost of lithium-based admixtures will be expensive, and we have to use a heavy dosage, so that will further increase the cost for lithium-based admixtures. Okay, and lithium-based solutions can also be used for ASR mitigation. That means when we already have ASR in concrete, if we apply the lithium-based solution, that may change the gel into a non-expansive nature, but the result may not be very clear. So depending on the situations. Okay. So, but anyway, lithium-based solution may be used if we already have ASR cracking in concrete. Mineral mixtures is very effective to reduce ASR. But of course, we need to mix mineral mixtures in fresh concrete. Okay, so before ASR occurs. Okay, so the reason for that have many different folds. The first fold is mineral mixture will reduce alkali concentration in cement, so that will dilute cement, reduce the pH level in pore solution, to reduce the amount of alkali. And we know polylytic reaction will also reduce the permeability of concrete. So the water will have a harder time to penetrate and cause the sweating. So that is also beneficial. And the third reason is because mineral mixture will generate non-expensive calcium, sodium, or potassium silicate hydrate. So that will be not expensive. Okay. So will cause non-expanding sodium, calcium, sodium, or potassium silicate hydrate instead of expanding sodium silicate hydrate. So make the gel non-expanding. Okay. So 3 reasons we use mineral mixtures to control ASR. All right, more details about mineral mixtures on ASR. This is about different type of mineral mixtures. Okay, so class F, flash. So class F flash usually works very well, and here is the reason. The calcium to silica ratio of CSH is lower when class F flash is used. Okay, and low calcium content CSH will absorb alkali hydroxide. So that will reduce alkali in the pore solution, so reduce the potential gel formation. Class C flash does not work as well because the CSH cannot absorb alkali hydroxide as effective. So this is a very detailed information. Okay. For silica film can absorb alkali hydroxide quickly, so that is also effective. But pay attention to silica film. We know silica film is very, very fine particles. Sometimes the fine silica particles will stick together and cause a very big chunk. And we know silica film, the chemical composition for that is reactive silica. So if a silica film is stick together, that will cause a lot of ASR. Okay, so be very careful about that. So make sure silica film is fully dispersed. Okay, other type of mineral mixtures such as metkaolin may also be working to reduce ASR. Even rice husk ash. Okay, here shows people using different dosage of rice husk ash to reduce ASR. You can see increase the dosage from 4% to 8% to 15%. We see less cracking due to ASR. Okay, so rice husk ash can also reduce the potential ASR. Okay, and here shows the result for slag. Okay, so we have different series of concrete with different percentage of slag, from 0 to 15 to 45 to 55 to 80% of slag. Okay, so what we can see here is we increase the dosage of slag, the expansion becomes smaller. Okay, but we have big jump between 45% and 55%. So that means maybe the best percentage for reduced ASR using slag is 55%. Okay. further increase slack, we will not see a big reduction in expansion. Okay, again, this is just an example of studying the effect of mineral mixtures on ASR. Okay. Again, this is just so scanning electron microscope. The cracking due to ASR, 45% of that. We see more cracking compared with 55% of slack. Okay. All right, so that's the end of today's lecture. We discussed durability in general, and the first durability issue is frost damage, and then we discuss ASI. Okay, in future lectures, we'll discuss soft-hit attack, corrosion of reinforcement, and other type of durability issues. Okay, so we have 2 more lectures on durability of concrete. All right, so let's see.